Welcome! This video explores how the natural response of a resistor-inductor circuit has a negative value for inductor voltage. The exploration clarifies both reference polarities and RL natural response. Given an initial condition inductor current oriented flowing downward through the inductor, we know that the current flow decays exponentially over time. This is natural response. Why will the voltage across the inductor be a negative value? From the inductor branch relationship equation, we know that the voltage across an ideal lumped element inductor is proportional to the derivative of the current through that inductor. The derivative of the current as a function of time gives us the slope of the current function. In this RL natural response example, the current is positively valued and decaying exponentially over time. The decreasing current function has a negative slope. The negative value of the derivative term of the inductor voltage equation makes the voltage across the inductor negative. How does this negative inductor voltage appear in the circuit analysis of this RL natural response? Look at the reference polarity, the direction of current flow relative to the inductor reference polarity. The voltage across the inductor is negative because the inductor current flows up through the resistor, dropping a voltage, Vres, that is opposite to the voltage reference polarity, V of t, for the inductor. Let's look at the details. When we put 5 volts across a resistor connected to ground, we get a positive current flowing down from the voltage to ground. This corresponds to a resistor reference polarity with the voltage plus sign at the top. Reference polarity relates to the branch relationship of a resistor. From Ohm's law, we know that the higher the positive voltage across the resistor, the higher the positive current flowing through the resistor. Conversely, if the voltage across a resistor is negative, that means that a negative current flows through the resistor. For an inductor, current flowing downward through the inductor also corresponds to a reference polarity with the voltage plus sign at the top. But different from a resistor, an inductor can have a voltage that is negative relative to the reference polarity. For natural response, the positive initial condition inductor current flowing clockwise around the loop and up through the resistor causes a voltage drop Vres across the resistor with the plus voltage at the bottom. This voltage Vres is the real voltage across the resistor and inductor in parallel. The voltage Vres has polarity opposite to the reference voltage V of t. The voltage across the inductor and resistor is negative.
Here is an LTspice circuit simulation of the RL natural response. The initial condition inductor current decays exponentially from 1 amp to 0. The resistor current is negative relative to the direction of the voltage reference polarity V sub RL set by the inductor current with the plus at the top. The resistor current goes from negative 1 amp to 0. Matching the polarity of the resistor current, the voltage V sub RL across both the resistor and the inductor is negative, going from minus 20 volts to 0.
Reference polarity appears when using KVL, Kirchhoff's voltage law. To start, there is only one voltage and it drops across both the resistor and the inductor in parallel. the reference polarities of V sub R and V sub L equal to one another correspond to positive currents flowing downward through each circuit element, the resistor and the inductor. I sub R and I sub L are opposite one another. Write Kirchhoff's voltage law for this circuit, starting in the upper left and proceeding counterclockwise around the loop, as shown by the red dashed arrows. This voltage summation establishes a reference polarity where V1 and V2 are both positive in the KVL equation V1 plus V2 equals 0. Going into more detail on this analysis, relate V1 to V sub R and V2 to V sub L. The polarity of V1 matches the polarity of V sub R, so the V1 term in the KVL equation can be replaced with V sub R. The V sub R reference polarity includes current I sub R going counterclockwise around the loop, which also matches the current polarity of V1. Continuing around the loop from the resistor and going up through the inductor, the polarity of V2 is opposite of the reference polarity V sub L of the inductor. The second term in the KVL equation is negative V sub L. Notice how V sub R minus V sub L equals 0, and the direction of the current for V2 and for V sub L are different from one another. Substitute the resistor and inductor branch relationship equations into the KVL equation. We see the difference in current direction between the two currents. The Ohm's law resistor term in the KVL equation refers to I sub R, and the inductor term refers to I sub L. In the KVL equation, V sub R minus V sub L equals 0. The inductor voltage term corresponds to the reference polarity of the inductor, with current I sub L flowing downward. If one changes the reference polarity of the inductor term in the KVL equation to the polarity of V2 by substituting I sub R in for I sub L, this polarity now corresponds to positive current going up through the inductor. The KVL equation changes to V sub R plus V sub L because the inductor polarity now matches the V2 polarity. Now we see the negative inductor voltage that was the starting topic of this lesson. If we have positive current down through the resistor corresponding to positive V sub R, we can change the inductor branch relationship equation from inductor current to resistor current, and we get negative inductor voltage V sub L. In practice, we see how we can directly write the KVL equation V sub R plus V sub L if we reference the counterclockwise current I sub R right away. If we go back to the mixed current equation and instead replace the resistor current I sub R with I sub L, we get the same negative inductor voltage result that we got with both terms using I sub R for current direction. This final case, using I sub L, exactly matches the original example where positive current flowing down through the inductor flows up through the resistor and drops a negative voltage across the resistor and the inductor. Using I sub L also corresponds to writing KVL in the clockwise direction.
Here is the final test question. We started out saying that the voltage across the resistor equals the voltage across the inductor. Those two voltages are in parallel, so they must be the same. Why then do we also see the resistor and inductor voltages opposite one another in previous slides and in the simulation example? How can V sub R equal negative V sub L now, when V sub R and V sub L were previously equal?
The answer is in the reference polarity. Look at the direction of the current. V sub R equal to V sub L corresponds to resistor and inductor currents that are opposite one another in the circuit. The equality of V sub R and V sub L depends upon opposing current reference directions. V sub R equal to negative V sub L corresponds to equations referencing one loop current direction around the whole loop. The current can go in either direction, clockwise in the light green box on the right, or counterclockwise in the yellow box on the left. This slide summarizes two reference polarities, two ways to set up the equations that solve the circuit. Both ways show that the voltage across the inductor is negative the voltage across the resistor. When working with Kirchhoff's laws and circuit analysis, pay close attention to which expressions for voltage and current presume which reference polarities. These modeling polarities also show up in the subscripts for voltages and currents. The equations and the Kirchhoff's voltage law in this lesson overlap many of the derivation steps for RL natural response. But the focus here is the reference polarity in circuit theory derivation setups and comparison of different setups.
Thank you for watching and learning with us.